Morning, everybody. Mr. Stewart here, and welcome to the screencast on experimental probability. In fact, this is a follow-up, everybody, to what we did last week, or rather this week. It's been crazy with all the snow days over the last couple of days. So recall the exercise regarding catch and release of the different species of fish and what we had determined experimentally. So you can see here, when we compared the number of trials, that is, when we were catching a specific species and comparing to the total, we came up with these three ratios here, the bottom left side of the screen. Okay, and then we had also converted those to a decimal ratio, as you can see here in green. Okay, over here on the right-hand side, this is the theoretical or the accepted probability. Okay, so these were the actual ratios that were set prior to the simulation. And as you can see, on the basis of these decimal ratios, they are very close to the experimental ones here. Okay, so the conclusion from there, and this happens with many real-world phenomena, is that as you increase the number of trials in your experiment, you're going to approach the theoretical probability. Okay. So moving forward, what we did and what you had done is you had taken the theoretical probability, you took those ratios and you were applying them to this particular question. And this is a sample of the work that has gone up in our room. So recall that we were looking for, we had a population of 21,000 fish, and we wanted to know those that were red and blue. Okay, so over here, we wrote down the various ratios or the probabilities of catching any one of those particular species. Okay. So having a look over here, here's a sample of student work. So what you can see is they have, of course, written down the given information, which is always a great idea. And over here on the left-hand side, okay, what they've done, that is step number one. I'm just going to highlight this here, is they decided to take the population and divide it by 15. Okay, so in effect, what that did was it allowed them to find 1/15 of the population. Okay, so it allowed them to find 1/15. Now, because they were looking for the probability of red, what they then did was they multiplied that result by 5. Okay, so they multiplied 1/15 by 5, which gave them the 5/15 ratio. Okay, so if you follow through here with the calculation, that's 1400 by 5, which gives you 7,000 red fish, or otherwise carp. Similarly, they did the same thing. Again, you can see how they took a 15th of 21,000, so 1/15, and then they tripled that, and that gave them 3/15, or 4,200 fish. Okay, so that technique, that is something known as using fractions as an operator. Okay, so using multiplication as an operation. Over here on the right-hand side, here's another strategy. Here's a group of students who had used equivalent fractions to solve a proportion. So first, you can see here is they had determined, okay, a 15th of 21,000. And in doing so, what they were trying to do was they wanted to figure out what is that multiplier. So what is this constant that I'm multiplying by, okay, to produce 21,000? So you can see how they've multiplied the 15 by the 1400, and what they've done to the bottom of the proportion, they've done to the top, and we're able to come up with a value. Okay, and they have, let's see, they have 4,800. Okay, now that's a different kind of question. That would involve the probability of y being used. Okay, so just a small misinterpretation of the problem, but you can see another way of arriving at it. But they did carry on with excellence here to finish the job. So you can see how they've done the same thing here and here, using both the probability of red, that ratio, and the probability of blue in the bottom in order to set up a proportion to solve for the required population values. That's not the only sample or way. There are different ways of representing it and different ways of checking your work. Here's another group. They did the same thing. They found a 15th, and they then went through and multiplied, as you can see here, and here, and here, those particular values, that is the 1400, to arrive at the answers of 42, as well as, there's a different value here, 7,000. Okay, so you can also see they went one more step, and what they wanted to do, okay, was to determine the decimal ratio. Okay, so here's a decimal ratio. And the reason why they were doing that, and they could probably tell you this, okay, is when they went to check their work, okay, this was a check they had done, and one of the only samples where I saw a check for reasonableness being done, and it's always a good idea when problem solving. They did two things. One, they tried adding up and did, okay, so they took the fractions, so this one, and this one. And what they did is they added those in order to see if they are able to arrive at one whole. So they were able to determine that that's 21,000 over 21,000, which is 100%. So they've accounted for all of the fish. Okay, so all the probabilities need to add up to 100%. And you can see that here too. If you were to add 7/15, 5/15, and 3/15, you'd have a total of 15/15, which is 1 or 100%. Okay. They also added their decimal ratios. So 0.2, 0.33, and 0.46. And due to the rounding error here, right, approximately 0.33, they ended up with 0.99 as a ratio, but otherwise equal to 1. Okay. So great technique and good to check your work. Here's another quick sample. Again, you're going to see a lot of similarities here with the other ones, and you can see that this student has chosen to use the decimal ratio. Okay, so the required number of fish, okay, so this would be the number of red fish here, so red equals. You can see their value is just a little bit off, and that's probably due to the rounding error. So you'd have to use the fraction 5/15 or 1/3, or add more decimal places to the calculation. Okay, and then over here is the number of bluefish, which you can see is worked out because the decimal ratio is exact. It's not approximate. All right, let's see where we are with this. Up to 8 minutes and 45, so we do have a little bit more, guys. So we'll try to keep the video short so that you can be more active in your work. I do have another sample. I do want to share that because it's really important. Here's another great one. This student here has chosen to use the experimental ratios. Okay, so their experimental ratio would approximate the theoretical. Okay, so the experimental approximates the theoretical ratio for red fish at 5/15. Okay, so what they've done is they've taken, let's go back and quickly grab a hold of that value. This might be from another, here it is, 155 over 355. So let's have a look at that. I guess this must be from the second class's data because the 114 is here. But anyhow, same principle. They've taken the denominator of the experimental ratio of 355 and have figured out that 59.1 groups of 355 will fit into 21,000. And they're using that, as you can see here, as their multiplier. Okay, so they're using an equivalent fraction, just like the other group had done, to come up with their total. Okay, and of course the numbers are going to be a bit different because of the experimental value, and also different because it's from a different class set. Okay, so lots of great opportunities. And over here, what I had done with the student was said, let's compare. So we took the experimental ratio, the theoretical ratio, and worked our way through to do a comparison. All right. So what I would ask you to do today, here's kind of the newish learning, but it's really something you've done before, and I just want to pick your brain and see what you can do with it. So we'll need to pause the video to give you some think time, and then we'll come back and you can either discuss with your supply teacher and or play on and see a couple of ideas that I've posted. So I want to know, what do you notice about the following? Well, playing the video on, you may have noticed that these particular ratios, okay, are what we say equivalent. Okay, so this ratio and this one here, they are equivalent ratios, so they're equal. Okay, so equivalent ratios. Now, given the fact that I'm writing on the screen with ink, you might hear a bit of tapping in the background. Okay, so it's just how the pen interacts with the screen. So you can see that by multiplying, okay, this particular ratio, 9 to 6 to 30, which is something that may have come up in your discussion, if I were to multiply that by a third, so take a third of every number, I'll produce the 3 to 10, 2 to 10 ratio. Alternatively, you may have talked about one being 3 times the other. So if I take that ratio and I were to triple that, I'd produce the other one, 9 to 6 to 30. Something else too that we can do now is, because they're equivalent, we can write the following statements. Okay, so here are just a couple of ways to represent the ratio, but in a fraction form. So this is called a proportion. That is an equation with fractions, equivalent fractions. So we could write it as 9 over 3 is equal to 6 over 2 is equal to 10 over 30 over 10. Okay, or alternatively, okay, you can see the equivalence in that. We could write it as 9. Let's see here now. How did I want to write that down, guys? Actually, on second thought, I'm going to save that for the next slide. So let's let that be for now. Okay, so let's move on. So what I would like for you to do with this is to solve the following ratio. So we're nearing about the 15-minute mark. So we're going to try to end it there so you can get on with your work. So same ratios, okay, and this might seem kind of silly to use the same ones, but I do want to be able to connect it back to what you just saw. So these ratios, saying that if they are equivalent, and let's just say that they are, okay, is to solve for x and y. Now there's different ways of doing that. Okay, so you can look at the information you're given, and we do know that the 2 and the 6, okay, they form one complete ratio, so you can use that constant of proportionality. So either multiplying by a third this way, or multiply by 3 one way, and multiply by a third this way. Alternatively, you might want to do it this way too, especially for some more difficult problems where the numbers aren't quite as nice to work with. So you can take the ratio, okay, and notice back here where I kind of paused and sort of was deliberating where I wanted to go with it. You can actually take a piece of this at a time and just work with it, okay? Right? Or you could work with this one. So if you have any unknown piece of information, you can simply solve. So for instance, let's take the x to 6 and represent that as a fraction. And we can set that equal to 3 to 2. Okay, so you can use the constant of proportionality, the 1/3 or the 3, or you can do something like the following. You can choose to solve the equation by clearing the fraction. Okay, so what we're going to do here is take 6 1/6 of the answer. Okay, so you might have seen that in other courses as being called clearing the denominator or canceling. So 6 goes into 6 once, and that leaves us with the answer x. And what you do to one side, you do to the other. So multiply both sides by 6. So that will give you 18 over 2, or also 2 will fit into 6 3 times, and you're left with 3 by 3, which gives you a value of 9, which is the answer that we had previously. Okay. On the other side of the fence, we have to solve for y. Now, it's always good to use given information, especially if you end up rounding an answer in some other problem. So for this one, we'll start out the same way. Okay, so we're going to use the unknown is 30 to y. Okay, so 30 over y is equivalent to another ratio we have been given, which is 6 over 2. Okay. Now, there's many ways to solve this one, but what I would recommend, okay, is if you're using the technique of clearing the denominator, it is appropriate to produce a similar ratio by inverting each of the fractions, okay, because it doesn't change the meaning whatsoever. Those are equivalent ratios, okay? Y is going to take on the same value. The benefit to that is instead of trying to clear a variable, we're going to clear this whole number value of 30. And what we do to one side, we do to the other. And through canceling, 30 goes into itself once, 6 into 35 times, and we're left with 2 times 5. So in other words, y is equal to 10. And you can see, just to verify, that that is true. Right? Back here, I'm just going to highlight these values. So we'd solve for that, we'd solve for this one as well. Okay? So that concludes the video. So your next steps are to move on into, let's see here. This was the problem that we were given in class, and that one there, we had just done a little background work for that here. So I would have you take on this particular question here, use that concept of ratios or equivalent ratios that you just saw modeled, and in your notebook and or on the lesson sheet that came out last week, rather 2 days ago, is to draw up a solution to this one here.